Okay, good morning, everyone. Good morning, everyone. Today we'll begin section 11.5, measures of central tendency and variation. A lot of the stuff you have seen before, so a lot of it will be quite easy. And then tomorrow we'll look at outliers. Vocab terms, expected value, probability distribution, variance, and standard deviation. Those are going to be new terms to you, something you haven't seen before. But you have seen, and they didn't list this as vocab terms because they assume you already know it, and I'm sure you do. Vocab terms mean or average, median, and mode. So recall that the mean or average, median, and mode are measures of central tendency, values that describe the center of a data set. The mean or average is the sum of values in the data set divided by the number of values. Mean or average means the same. It is often represented as X bar. The median is a middle value or the mean of two middle values when the set is ordered numerically. So if you have an odd number of items, if you have like 7 items in a data set, the median will be the number right in the middle. So you'll have first 3 numbers, and then you'll have your median, and then you'll have your other 3 numbers. So the median is always a number right in the middle. So that's for an odd data set. But if you have an even data set, for example, you have 8. So you have 4 items. So you have 4 items on one side and 4 items on the other side. So that's an even number of items. The median, you'd have to average the 2 right in the middle. Okay, so the mode is the value or values that occur most often. A data set may have one mode, no mode, or several. So let's take a look at all of this. A lot of this you've done before. Find the mean, median, mode of the data set. So we have the values 3, 0, 2, 0, 1, 2, 4. This represents the number of deers at a feeder each hour. On average, we sum up the values, divide by how many we have, and on average, or the mean, there was 1.7 deers at the feeder each hour. The median, we have to order the data from least to greatest. You always have to do that with the median. Now what do we have? We have 6, 7. We have 7 data items, so the median is going to be the number right in the middle. We have 3 items on one side and 3 on the other, and then the median is a number right in the middle. The mode is the one that occurs most frequently, the number. So in this case, is bimodal. We have 2 numbers, 0 and 2. Let's look at this one. Find the mean, median, and mode of the data set. Here we have 4 items. We sum them up. We get 26. 26 divided by 4 is 6.5. The median, we order the items from least to greatest. Because we have an even number of items, we have to average the 2 to get the median. So the median is 7, and there is no mode. Okay, and then one more. Okay, so we have the numbers 2, 5, 6, 2, 6. We sum them up. We get 21. We divide by how many numbers we have, which are 5. We order the items from least to greatest. We have an odd number of items, so the median is going to be the number right in the middle, which is 5. And then this again is bimodal. We have 2 modes, 2 and 6. On your homework, please show doing this work here. Show doing that work. All right, now a weighted average is a mean calculated by using frequencies of data values. Frequencies meaning how often or how many times it occurred. How many times that particular item occurred. So suppose that we have 30 movies and they're rated as follows. 8 movies had a 4-star rating and 12 movies 3 stars. 7 movies had a 2-star rating. 2 movies had 1-star rating, and then 1 movie had no stars. Bad movie. Anyway, so we're going to find a weighted average of the ratings for these movies. Well, we wouldn't take 4 and then 3 and then 2 and then 1 and 0. We wouldn't add those up. And so 4 and 3 is 7, and 7 plus 3 is 10. We wouldn't take 10 and divide it by the 5 ratings to get to. That would not be our average, because we have not taken into account that more movies, 8 movies, had a 4-star rating, and then 12 movies had a 3-star rating. Okay, so we would take a weighted average, and your GPA is a weighted average, right? Some of you may take AP classes, and they're weighted at a higher rate. So your GPA is a weighted average. So how do we calculate a weighted average? Well, what we say is that we had 8 movies and they were rated 4 stars, and then we had 12 movies, they were rated 3. So you see, we're giving more weight to those movies that had a higher rating. We're giving more weight. And then we had 7 movies that were rated 2, 2 movies rated 1, and then we had 1 movie that was rated 0. So what we do, we add up those products, we get 84, and now we divide by the number of movies we had. So we had a 2.8 star rating, 2.8. You see, again, when I did the other average, what did I have? I had 10 divided by 5 equals 2. That would be wrong. The weighted average was 2.8 stars. Not 2, and why? Well, because we had a lot of movies that had 4 and 3 star ratings. So, weighted average. Let's look at another example here. For numerical data, the weighted average of all the outcomes is called the expected value for that experiment. The probability distribution for an experiment is the function that pairs each outcome with this probability. So let me explain. We'll take a look. So here we have the probability distribution of successful free throws for practice set is given below. Find the expected number of successes for one set. So here we see that the probability that someone had 0 free throws in that set was 3/20, or 15%. 15% probability. The probability that someone had 1 free throw was again 3/20, or 15%. The probability that someone had 2 free throws was 1/5, or 20%. And then the probability someone had 3 free throws was 1/2, or 1/2%, 50%. Well, in these probabilities, they would have to sum to 1, and they do. Okay? But the probability distribution, to go back, is an experiment, is a function that pairs each outcome of 0, with this probability, 15%. Okay? Pairs each outcome 1 with this probability, 15%. Pairs each outcome 2 with this probability, 20%. And then pairs each outcome 3 with this probability, 50%. Oops. Right, so that's what a probability distribution is. And in probability distributions, when you add up all the probabilities, they should sum to 1. Okay, so how would we find the expected value then? What would be the expected number of free throws in a given data set? Well, we have to take each outcome, 0, for example, and multiply it by its probability. Each outcome, 1, and multiply it by its probability. Each outcome, 2, and multiply it by its probability. Each outcome, 3, and multiply it by its probability. In terms of fractions, well, that would give us 0 plus 3/20, plus 2/5, plus 3/2. And then if we add those fractions, remembering we have to have a common denominator, we'd have 3/20, 8/20, plus 30/20, which is 41/20. So the expected number of free throws would be 2.05. And that makes sense, because The larger number of free throws, 2 or 3, are weighted more heavily. 2 has a weight of 20%, and then 3 has a weight of 50%. So you would expect that the expected number of free throws would be greater than 2, or about 2, so 2.05. Let's look at another one. The probability distribution of the number of accidents in a week at an intersection based upon past data is given below. Find the expected number of accidents for 1 week. How many accidents would you expect in 1 week? So we see that when we had 0 accidents, well, that happens with a probability of 0.7, 75%. When we have 1 accident, well, that happened at a probability of 15%. 2 accidents, probability of 0.08%, or 8%, and then 3 accidents with a probability of 2%. So we would expect that the expected number of accidents should be very close to around 0, because the probability of having 0 accidents is a lot higher. So what do? We take each outcome, 0, and we multiply it by its probability. Each outcome, 1, and we multiply it by its probability. Each outcome, 2, and we multiply it by its probability. And each outcome, 3, and we multiply it by its probability. So the expected number of accidents is 0.37, which we would expect, because 75% of the time we have 0 accidents. Again, that's expected value. Okay, a box and whisker plot, and I believe you guys have done this before, shows a spread. Okay, so these we were looking at measures of central tendency, everything we've done before. Expected value, mean, median, and mode. Now we're going to look at measures of variation. A box and whisker plot will give you something about the variation of a data set. So a box and whisker plot shows the spread of data set. It displays 5 key points: the minimum value, the maximum value, the median, the number right in the middle, and then the first and third quartiles. And why are they called the first and third quartiles? Well, because in a box and whisker plot, between the median and the first quartile, we have 25% of the data. Between the first and the median, we have 25% of the data. Between the median and the third quartile, we have 25% of the data. And then between the third and the maximum, we have 25% of the data. So that's why they're called the first and third quartile. First quartile, we have 25%. The third quartile, we'd have a total of 75%. 25, 25, and 25. That's why they're called the first and the third quartile. First quartile meaning we'll have 25% of the data. Third quartile meaning we'll have 75%. So we're 25, 25, and 25. And then we have something called the interquartile range, which gives us 50% of our data. 50%, 25 and 25. The interquartile range is always the third quartile minus the first quartile. All right, so let's take a look. Oh, so they mentioned the quartiles are the medians of the lower and upper halves of the data set. If there are an odd number of data values, do not include the median in either the first or the third quartile. We'll see that. If there's an odd number of data items, remember, the median is always the number right in the middle. So this would be like our first quartile, and that would be our third. So if there are odd number of data values, do not include the median in either half. So we wouldn't include it in the first half, okay, or we wouldn't include it in the upper half. We'll see that. All right, the interquartile range, or IQR, is the difference between the first and the third quartiles. It represents 50% of the data, which is what I just said. So example, making a box and whisker plot and finding the interquartile range. So we have this data set 6, 8, 7, 5, 10, 6, 9, 8, 4. We have to order the data from least to greatest to find our median. Let's see here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 items. So the median will be the number right in the middle. So let's find the maximum, minimum, median, and quartiles. Okay, so when we order the data, the median is going to be the number right in the middle. We have 9 items, so the median is going to be 7. And then we have the lower half, and then we have the upper half. Now the first quartile, we have 4 items here. So we have to find the median there. We have an even number of items, so we have to average those two. And then the upper quartile, we have 4 items, and again, to find the median, we have to average those two. So there, now we can make our box and whisker plot. We have the minimum, we have the first quartile, we have the median, we have the third quartile, and the maximum. And that's why that is called. Okay, so that's why we call it the, we'll make the box and whisker plot now. So let's do this. So draw a box and whisker plot. Draw a number line and plot a point above each of the 5 values. Then draw a box from the first quartile to the third quartile with a line segment through the median. Draw whiskers from the box to the minimum and max. So this is what they did. So if you go back up here, our median was 7, and there's 7 there. Our first quartile was 5.5, so they drew a line there. Okay, and then our other the third quartile was 8.5, and they drew a line there, and then we draw a box around everything. That represents 50% of the data set, and then we list our minimum, which was 4, and our maximum, which was 10. So there. I always encourage students just to label, so that's, so you can see that box and whisker plot. And then the interquartile range is Q3, which is 8.5, minus Q1, 5.5 or 3. Okay, so let's look at another one. Make a box and whisker plot. Plot the data, find the interquartile range. So we have these values. We order them from least to greatest. Okay, we have an even number of items, right? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We have an even number of items. So in order to find the median, we would have to average the two numbers right in the middle. 14 and 14 gives us an average of 14. So that's our median. Now for the first quartile, or the lower half, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 items. And so again, in order to find the first quartile, we'd have to average those 3. And then for the upper half, again, we have an even number of items. In order to find the third quartile, we have to average those 2. We have our minimum 11 and a maximum 23. So we draw our median line. And when you guys draw these things, you always want to make sure that your spacing is equal. Otherwise, you distort your box and whisker plot. So, in other words, what I mean by that is between each tick mark, it should represent equal spacing. So, equal spacing there. All right, so we had our median. So we draw a line at our median. 14, we draw a line at our first quartile. 13, a line at the third quartile. 18, we put a box around everything, and then we draw or plot our minimum, which is 11, maximum 18, and then we draw whiskers. The interquartile range is 18 minus 13, which is 5. Okay, so now things you've done before. I'm sure you guys have made Bos and whisker plots before. Everything we've done so far, you have done many times. Now we're going to introduce things that you haven't done before. Let's take a look at this. The data sets 19, 20, and 21, and 0, 20, and 40 have the same mean and median, but the sets are very different. Which one has more variation? Okay, one way we define variation, if you remember, was the range. So the range here would be the largest value minus the smallest. So 21 minus 19 equals 2. And the range here would be 40 minus 0 equals 40. So if I said which one has more variation, that's like saying which one is the range the largest. Well, certainly this one has a lot more variation. Okay, they may have the same mean and median, but the sets are very different. The way the data are spread out from the mean or median is important in the study of statistics. A measure of variation is a value that describes the spread of the data. The most commonly used measures of variation are the range, and I just did that, the interquartile range, which we did with Bos and whisker plots, and what we're going to learn today is the variance and standard deviation. The variance is denoted by, we call that sigma squared, or no, not sigma, rho squared, or yeah, this is actually the symbol rho squared. So is the average of the squared differences from the mean, and we'll see that here. The average of the squared differences from the mean. The standard deviation, denoted by that rho, is a square root of the variance and is one of the most important and useful measures of variation. So let's take a look at standard deviation. So here I've plotted what I assume would be the distribution of heights of various populations. So for example, for female gymnasts, I mean, they're pretty petite, right? You don't find many female gymnasts, Olympic gymnasts, which are very tall. So let's say here their average height, let's just say, would be about 4'8", 4'9". I just made this up, I don't know. About 4'9", 4 feet 9 inches. Okay, but their differences, the spread of their height, well, it may go anywhere from 4 inches or 4 feet 6 inches to 5 feet 4 inches. Okay, so the variation in their height just wouldn't be a lot. Let's say here then, let's say the standard deviation, and we'll say is 3 inches. 3 inches for female Olympic gymnasts. Now let's take a look at let's say here this is, I forgot to label this. This would be male NBA basketball players. Okay. And let's say here, you know, they're pretty tall. So let's say here their average height is like 6 feet 4 inches. But again, the distribution or spread in their height, it wouldn't be very large. It may go from anywhere from 6 feet to 6'8". And I'm sure there are some that are even taller than that. But again, let's say here their standard deviation would be 2.5 inches. But then when you take a look at the entire population, if you included everybody, their average height would be like 5 feet 8 inches. But the spread or variation in their height would be much larger. Let's say here that would be about 6 inches. Okay, so you see that the standard deviation is a useful measure of variation. It will tell you how much variation there is in a set of data. The larger the standard deviation, the greater the variation. Low standard deviations indicate that data are clustered in other measures of central tendency, like for female gymnasts or male NBA basketball players. Okay, whereas high standard deviations indicate that data are spread out from the center. Like if you took a look at the average height for the general population, for all population, it's going to be all over the place. The spread will be all over. So how do we find a variance in standard deviation? Well, first we have to find x bar, or the mean, or the average. Then we take the difference between each data value and the mean. We take that difference and we square it. And then we square it, and then we add up all the squares of the differences, and then we divide by the number of data values. And then to find the standard deviation, we just take the square root of the variance. So I'll go through these calculations. Well, here the symbol commonly used to represent the mean is x bar, or x bar. The symbol for standard, oops, I said rho, actually that's sigma. Yeah. The symbol for standard deviation is a lowercase Greek letter sigma. Okay. So standard deviation is sigma, variance is sigma squared, and then standard deviation is the square root of sigma squared. Right. So for example, finding the mean and standard deviation. So we have this set of data. We first have to find the mean. We get 7. That's step 1. Now we're going to have to, from each data value, that was 6, 8, 7, 5, 10, we're going to have to subtract the mean. So 6 minus 7 gives you -1. 8 minus 7, 1. 7 minus 7, 0. So that's the difference between each value and the mean. Then we take that difference, -1, and we square it. We get 1. 1 squared is 1. 0 squared is 0. -2 squared is 4. We take those differences and square them. And then we add them up. The differences squared. We add them up. We divide by how many we have, which is 9. And that gives us our variance. Now, that's our variance. To find a standard deviation, we take the square root of the variance. Take the square root of the variance. And you get 1.83. So the mean is 7 people, and the standard deviation is about 1.83 people. Let's look at another. Find the mean and the standard deviation for the data set of the number of elevator stops for several rides. So again, first we have to find the mean. We add up all those numbers. We have 10 numbers. We divide by 10. We get the mean 1.4. That's the average. Okay, now we have to find the difference between each data value, 0, 3, 1, 1, 0, 5, and the mean. So 0 minus 1.4 is -1.4. 3 minus 1.4 is 1.6. 1 minus 1.4 is -0.4. We do that for all the data values. We square it. -1.4 squared is 1.96. 1.6 squared is 2.56. We square all the differences. So now we add them up. We have to take those and we add them up. And then we divide by how many values we had, which is 10. That gives us our variance. And then to find the standard deviation, we take the square root. That gives you 1.6. So the mean was 1.4 stops, and the standard deviation was about 1.6 stops. Okay, so I'll show you how you can use Desmos to find the standard deviation. I don't generally require you to show your work calculating standard deviation because it's kind of tedious, but I will show you how you can use Desmos to do this. So I'm going to do it with this problem. Let's see here. Our data values were 0, 3, 1, 1, 0, 5, 1, 0, 3, 0. So I'm going to go out to Desmos. And here I'm in Desmos. So what you want to do, you want to click on that plus. we'll go to table, and then just x1, I'll just enter in those values I had. So 0 was 3, 1, 1, 0, 5, 1, 0, 3, 0. Okay, and then what I'll do is I'll go here to keypad. You want to go to functions. We're working with statistics. Oh, I'll show you. So I could actually find, we got a lot of things here. The mean, if I go mean, show you, you can go the mean, and it's going to, oops, let me back up there. I wanted to, oh, I got to click another, yeah, I got to go down there. So can't be in the table, you got to be outside the table. So once I was done with the table, then I just clicked there, and that gave me something else to do. So now let me go back. So functions, and then stats. In here, if I wanted to calculate the mean of that data set, x bar, well, I'm working with data x1, so I would just enter in x1. And there's my mean, and so that was the mean, right? 1.4. If I go back here, yep, 1.4. And then let's see here, if I go back here, what happens if I want to calculate, and if I wanted to calculate the median of that data set. Oops. Let me back up here. Okay, do another one. Okay, hit enter, press enter. I want to create another one of those rows there. And if I go here, okay, if I go back into stats, if I wanted to find a median, go median x1, there it was 1. So this is a good way to check your work. Let me hit another, press enter again. Function stats, what else? I can calculate the min and the max. But then the standard deviation for our purposes, you will want to use STD EVP, so standard deviation of the population. Standard deviation. You can calculate the variance too if you wanted to. Well, let me do that. Variance of x1, and what did we get? 2.933. I'm just curious to see if that's what, yeah. Okay, they're using, so we're not going to use that because they're using a different formula for the variance here. Okay, which is, should do more in statistics. But for standard deviation for our purposes, we'll want to use STD-EVP. Standard deviation of, well, let's standard deviation of a population. Here, let's try this one. STD EV population would have to subtract 1. They are using, so standard deviation x1. So let's go back here. Well, 1.6. So let's see here. Are they using standard deviation? Standard deviation P. 1.6. Okay, and that's what we got. 1.62. Okay, so 1.6. So what you'd have to use, don't want to use. So when you're calculating the standard deviation for our purposes, we'll have to use the standard deviation of the population. And so that will be STD-EVP. All right. So let me make a screen printing of this here so you guys know what to use. And so as you're doing your hand calculations, you can check your work. On a quiz or test, I actually allow you to use decimals when you're calculating the standard deviation. So you got your mean, which was 1.4, right? And then the median, which you didn't need in this case here, but I got it anyway. But then the standard deviation, you'll want to use standard deviation EVP, standard deviation of the population. Okay. Yeah, so do this. I'm calculating standard deviation by hand for homework, but on the quiz or test, you don't have to. You can just use decimals there to do that.